High above, the universe hides its strangest wonders. Neutron stars. Small as cities, yet powerful as suns, they twist light, time and gravity itself. Tonight, we uncover 100 incredible facts about these mysterious cosmic giants. Fact 1. The cosmic death that gives life. How neutron stars are born. Have you ever wondered what happens when a star dies? Not quietly, but in an explosion so powerful it outshines entire galaxies. It sounds like an ending, but in truth, it's the beginning of something new. When a massive star reaches the end of its life, it runs out of the fuel that has kept its heart burning. Hydrogen and helium slowly fused into heavier and heavier elements. The pressure that once balanced gravity begins to fade, and the star starts to fall in on itself. Its outer layers collapse inward, then rebound in a brilliant detonation called a supernova, a cosmic heartbeat that can light the sky for weeks. What remains after that brilliant flash is small, dense, and extraordinary, a neutron star, the collapsed heart of a once shining giant. Imagine something the size of a city, yet heavier than the sun. Inside, atoms have been crushed so tightly that protons and electrons merge into neutrons, matter packed beyond imagination. It's strange to think that death could create such beauty, but this is how the universe renews itself. The explosion scatters elements, iron, carbon, gold, across space, seeding new worlds and life yet to come. The quiet core left behind spins, radiates, and hums like a cosmic memory, a reminder that endings are never truly the end. Somewhere out there, another star is nearing its final breath. When it bursts, it too will leave behind a tiny ember of infinite weight, a neutron star born from destruction, carrying the echo of its parents' light into eternity. Fact 2. What's left after a supernova explosion? When a star dies in a supernova, the sky briefly blooms with impossible brightness. But after the fireworks fade, what remains is something hauntingly quiet, a ghost of a star transformed forever. For a few heartbeats of cosmic time, that explosion releases more energy than the star ever produced in its entire lifetime. Its outer layers are flung into space, becoming clouds of glowing gas, nebulae that will one day cradle new stars. Yet deep inside the blast, something survives. A dense core, crushed by its own gravity, endures the chaos. If the original star wasn't too massive, that core becomes a neutron star, an object so compact that a single teaspoon of it would outweigh mountains. If the star was larger still, gravity wins completely, and a black hole takes its place. The space left behind isn't empty. It's a canvas painted with colour and dust, where hydrogen mingles with the ashes of heavier elements. Over thousands of years, that debris drifts, cools, and eventually collapses again. The ashes of one generation forming the next. So what's left after a supernova? Not just fragments, but potential. A reminder that even in destruction, the universe finds ways to create. Every atom in your body, from the iron in your blood to the calcium in your bones, was once scattered from such an explosion. You are, in a quiet way, what's left after a supernova too. Fact 3. The collapsing core, gravity's final victory. There's a moment deep inside a dying star when everything begins to fall. The balance that once held it steady vanishes, and gravity, patient for millions of years, finally takes control. As fusion slows, the outward pressure keeping the star inflated weakens. The core, suddenly unsupported, collapses inward at a breathtaking speed, tens of thousands of kilometers per second. The heat surges to billions of degrees. Atoms shatter. Electrons are squeezed into protons, forming neutrons and releasing a storm of neutrinos that rush out through the collapsing layers. This is gravity's final victory, an unstoppable implosion that turns a sphere of fire into an object smaller than a city. The collapse halts only when matter becomes so tightly packed that quantum forces refuse to let it compress further. The result, a neutron star, a dense sphere of pure neutron matter. Outside, the collapsing layers crash against this newborn surface and rebound, igniting a shock wave that rips the star apart. The explosion we see from Earth is just the outer echo of that hidden battle. A battle that ends in silence, with gravity holding the final word. It's humbling to think that the same invisible force that keeps your feet on the ground can crush a star to the edge of physics. In that collapse, gravity doesn't destroy, it transforms. It takes chaos, compresses it, and leaves behind something impossibly stable. A heart that beats no more, yet still radiates light across the cosmos. Fact 4. How a star's mass decides its fate. From the moment a star is born, its destiny is written in its weight. Mass is its secret storyteller, the quiet force that decides whether it will fade gently or end in fire. Small stars live long, gentle lives. They sip their fuel slowly, shining for trillions of years before cooling into dim embers called white dwarfs. But the massive ones, the giants 10 or 20 times heavier than the sun, burn fast and bright, their cores like roaring furnaces. They live brief, brilliant lives, then meet spectacular ends. When fusion in a massive star's heart stops, gravity pulls inward with no resistance left to fight it. If the star isn't too heavy, its collapse stops at the neutron stage, forming a neutron star. But if it's more massive still, even neutrons can't hold up against the crushing force, and the star collapses further into a black hole. It's strange how something as simple as mass can decide such grand outcomes. The difference between eternal light and eternal darkness may be just a few solar weights. Every star, no matter how heavy, eventually gives back to the universe, scattering the materials for new suns, new planets, and perhaps new lives. Mass sets the path, but not the meaning. Even the smallest star leaves behind light that travels forever. Fact 5. The moment a neutron star is formed. In the heart of a dying star, there's a moment so brief it almost escapes time. The instant when collapse turns into creation. The core, crushed under unimaginable pressure, shrinks until neutrons stand shoulder to shoulder, refusing to be squeezed further. The collapse halts suddenly, like a heartbeat caught mid-pulse. The rebounding shock tears through the star's outer layers, triggering the brilliant flash of a supernova. And in that silence that follows, amid the drifting fire and fading light, a neutron star is born. It spins rapidly, carrying the angular momentum of its once enormous parent. Magnetic fields intensify, wrapping around it like glowing threads. Temperatures soar to hundreds of billions of degrees, but quickly begin to cool as the newborn star settles into equilibrium. From the outside, it's no larger than a city, yet inside, matter has reached one of nature's final limits. No light escapes from within, only radiation from its hot surface and sometimes the rhythmic pulses of energy we detect from far away. That single moment of birth transforms the violent death of a star into a quiet, enduring signal. Long after its parent's light fades, the neutron star continues to spin, whispering across the universe. It's the universe's way of saying that even in collapse something endures, not destruction, but a new kind of order, dense and dazzling, cradled by gravity and time itself. Fact 6. Why not every star becomes a neutron star? Not all stars are destined for a dramatic ending. Some fade quietly, like candles burning down to their final flicker. Others collapse so completely that even light can't escape. A neutron star's birth is a delicate balance, one reserved only for the few that are just the right size. A star's mass decides everything. If it's small, like our sun, it spends its life calmly fusing hydrogen into helium. Over billions of years, it swells into a red giant, shedding its outer layers until only a glowing core remains, a white dwarf, gentle and stable, slowly cooling in the dark. There's no explosion, no collapse, no neutron star. If it's too massive, perhaps 30 times heavier than the Sun, gravity becomes unstoppable. When its core collapses, not even neutron pressure can resist the pull. The star keeps falling inward, crossing an invisible boundary where time and space fold in on themselves, and a black hole is born. Only stars that live in the middle, massive enough to explode, but not too massive to crush themselves completely, give rise to neutron stars. It's a narrow window in the cosmic scale, a perfect point between stillness and oblivion. So most stars never know that fate. They end quietly or vanish entirely. But for those few that find themselves balanced on that thin edge between survival and collapse, the result is extraordinary. A city-sized remnant of impossible density spinning forever, carrying the memory of its former brilliance into eternity. Fact 7. The balance between gravity and quantum pressure. At the heart of every neutron star lies an invisible struggle, a cosmic standoff between gravity, which pulls everything inward, and quantum pressure, which pushes back. Gravity is relentless. It wants to crush matter until there's no space left between the particles. Inside a dying star, when fusion ends, gravity begins its slow, unstoppable victory. The star collapses, its atoms pressed tighter and tighter, until the normal forces of matter break down. But deep inside, a strange resistance awakens, the degeneracy pressure of neutrons. It's not a physical wall, but a law of quantum mechanics. Particles, like people in a crowded room, refuse to occupy the same space at the same time. No matter how strong gravity becomes, it can't make two identical particles stand in the same spot. That invisible defiance is what holds a neutron star together. Gravity compresses, quantum rules resist. The star teeters on the very edge of collapse, balanced perfectly between creation and destruction. It neither expands nor implodes further. It simply endures, forever caught between two fundamental truths of the universe. It's humbling to realize that such a small, unseen law, the refusal of particles to share space, can hold back something as mighty as gravity itself. In that delicate balance, the universe reveals one of its quietest miracles, the power of structure within chaos, order born from pressure, stillness born from tension. Fact 8. The difference between neutron stars and black holes. At first glance, neutron stars and black holes seem like twins, both born from the collapse of dying stars, but their destinies diverge at the smallest difference in mass, leading them down two entirely different paths. When a star collapses after a supernova, gravity tries to crush it endlessly. If the collapsing core is light enough, the neutrons inside push back, forming a dense, stable sphere known as a neutron star. Its surface is solid, though unimaginably hot and dense, and it still radiates light and energy. But if the core is heavier than about 3 times the mass of our Sun, even neutrons cannot resist the pull. The collapse continues until gravity compresses everything into a single point, a singularity, hidden behind an event horizon, the boundary from which not even light can escape. That's a black hole. So, a neutron star is the last stand before total collapse, matter held up by quantum laws, visible to the universe. A black hole is what happens when those laws are finally overpowered, and yet they are bound by kinship. Both are remnants of life and death, extreme ends of matter itself. One whispers through pulses and radiation, the other remains silent, a shadow on space-time. Together they mark the limits of what the universe allows, the edge where physics bends toward mystery. Fact 9. The first neutron star ever discovered. It began, as many great discoveries do, with something strange, a signal that didn't seem to make sense. In 1967, a young graduate student named Jocelyn Bell Burnell was studying radio waves from deep space. Her equipment traced long, continuous lines on paper, the faint heartbeat of the cosmos. But one day, she noticed a tiny blip repeating with perfect precision. Every 1.337 seconds, a pulse. Steady, unwavering like a cosmic clock. At first she thought it was interference, maybe a satellite or an error in the wires. But the signal kept coming, night after night, from the same point in the sky. It was too regular, too perfect. Her team half-jokingly labelled it LGM-1, short for Little Green Men, because no known natural object behaved like that. Soon, more signals appeared, from different parts of the sky. The mystery deepened, then revealed itself. These were not messages, but pulsars, rapidly spinning neutron stars emitting beams of radiation from their magnetic poles. As they rotated, the beams swept past Earth like a lighthouse, creating those rhythmic blips. Jocelyn Bell Burnell had unknowingly discovered the first neutron star, a city-sized remnant of a supernova, spinning dozens of times per second, whispering across light-years of space. That discovery reshaped astrophysics forever. It proved that neutron stars weren't just theory. They were real, alive in the sky, and calling to us in pulses of time. Fact 10. The connection between neutron stars and the life cycle of the universe. The story of a neutron star isn't just the story of death. It's part of a larger, endless rhythm, the universe creating, collapsing, and beginning again. When a massive star ends its life, its explosion scatters elements across space: gold, silver, oxygen, carbon. Those atoms drift and mingle with cosmic dust, forming the clouds from which new stars and planets are born. In that way, the life of one star becomes the seed for countless others. Neutron stars play a crucial role in this grand cycle. When two of them collide, their violent merger sends ripples through space-time, gravitational waves, and for a moment, they shine brighter than galaxies. In that burst, they forge the heaviest elements known: gold, platinum, uranium. Without those collisions, the universe would be a simpler, poorer place. No jewelry, no technology, no complex worlds. Every neutron star is a relic of creation's recycling, a reminder that the universe wastes nothing. Even in silence, even in collapse, it gives back. Somewhere. Perhaps right now the atoms that once belonged to a long-dead neutron star drift through a nebula, waiting to be gathered into a new sun, a new planet, or perhaps the breath of someone gazing up at the stars. In the end, the life cycle of the universe is not about endings at all. It's a loop of transformation, a cosmic heartbeat, steady and eternal, where even death glows softly with the promise of renewal. Fact 11. The role of iron in a star's death. Every star has a heart made of fire, a furnace that turns simple atoms into something greater. For millions of years, hydrogen becomes helium, helium becomes carbon, and heavier elements form in layers like rings of time. But somewhere near the end of a massive star's life, the fire reaches a limit, and that limit is iron. Iron is different. It cannot give off energy through fusion. Instead of feeding the flame, it drains it. When iron builds up in the core, the star's inner fire begins to fade. The outward pressure that held gravity at bay weakens, and a quiet imbalance begins. Gravity senses the hesitation and starts to win. The core collapses. The outer layers fall inward and rebound violently, sparking the greatest fireworks in the universe, a supernova. All because the star's heart filled with iron, the one element it could not burn. It's almost poetic. The very metal that forms in the final heartbeat of a dying star is also what makes our blood red, our planet strong, and our tools possible. The iron in your body was born in the death throes of a long-forgotten giant. When you hold something made of metal, you're holding the last breath of a star. In the end, Iron is both a star's downfall and its gift, the quiet messenger of endings that give rise to beginnings. Fact 12. What makes the explosion so bright? When a massive star dies, it doesn't fade gently. It bursts into brilliance so intense that it can outshine entire galaxies. But what makes this final flare so bright? It begins with collapse. The star's core implodes, and the shockwave races outward. In a fraction of a second, temperatures soar to hundreds of billions of degrees. Matter is torn apart and transformed into light, energy, and waves of invisible particles called neutrinos, released in unimaginable numbers. As the shockwave punches through the outer layers, the star's gases ignite in one last radiant blaze. The brightness isn't from fire as we know it, but from atoms breaking, fusing, and scattering light in every direction. Hydrogen, helium, and heavy elements glow with spectral colours, a rainbow of destruction that can be seen across the cosmos. For days or even weeks, the dying star shines with the power of billions of suns, and then slowly it dims, leaving behind only a faint nebula, and at the centre, a newborn neutron star or black hole. The brilliance of a supernova is not just its energy, it's its generosity. It throws light into the dark, metal into emptiness, memory into silence. It's the universe's way of saying farewell. A flash so bright we can still see it centuries later. Fact 13. The energy released in a single supernova. It's almost impossible to imagine the power contained in a single star's death. When a supernova erupts, it releases more energy in one instant than our sun will emit in its entire lifetime. During the collapse, gravity squeezes the core into a dense neutron star, matter packed tighter than atomic nuclei. The sudden stop of that collapse sends a shock wave hurtling outward, blasting the star's outer layers into space. The explosion releases about 1034 joules of energy, roughly 1 trillion times the total energy humanity has ever produced. Most of that power doesn't appear as light, but as neutrinos, ghostly particles that flood the universe, carrying away the heat of creation. Only a small fraction of the total energy shines visibly, yet even that is dazzling enough to illuminate galaxies far away. That burst of power reshapes the space around it. It sweeps nearby gas into waves that will one day form new stars and planets. It spreads iron, gold, and oxygen into the interstellar medium, cosmic ingredients for everything yet to come. To witness a supernova is to glimpse the raw heart of physics itself, gravity collapsing, atoms fusing, and the laws of nature colliding in a single act of transformation. From chaos comes clarity, from destruction, light. The star ends, but its energy lives on in everything it touches, even, perhaps, in us. Fact 14. How long it takes for a neutron star to form. When a massive star collapses, the transition from life to neutron star happens faster than a heartbeat. In less than a second, gravity crushes the core to a fraction of its size, forcing electrons and protons to merge into neutrons. In that instant, a new kind of star is born. The outer layers, however, take longer to respond. They crash inward, rebound, and explode outward as a supernova, a process that unfolds over minutes to hours. Meanwhile, deep inside, the newborn neutron star stabilizes, cooling from billions of degrees to millions, then settling into steady rotation. From a cosmic perspective, it's one of the quickest transformations imaginable. The life of a star condensed into a flash of violence and silence. Yet the consequences last for millions of years. The neutron star continues to spin, beam, and age long after the explosion fades. So while the creation itself is almost instantaneous, its story stretches endlessly. 1 second to be born, 1 billion years to endure. It's a reminder that even the fastest moments in the universe can leave echoes that outlast time itself. Fact 15. The silent aftermath. A new cosmic core remains. After the explosion fades and the gas clouds drift apart, a stillness returns to space. The fireworks are over, but something extraordinary remains. A tiny silent core pulsing softly in the dark. This is the neutron star. All that's left of a sun once millions of kilometers wide, now compressed into a sphere no larger than a city. Its surface glows faintly with residual heat. Its magnetic fields twist invisible lines through the void, and its spin carries the memory of the star that came before. Around it, the remnants of the supernova expand outward, delicate filaments of colour, gas and dust drifting through the black. These remnants will someday become the seeds of new stars, new worlds, and maybe even new life. But the neutron star stays where it was born, a quiet monument to both destruction and endurance. There's no sound in that silence, but if there were, it would be the soft hum of eternity, the vibration of matter pressed to its limit, refusing to vanish. The universe doesn't mourn, it transforms. The star is gone, but its heart remains, dense, steady, and timeless, holding the memory of its light within its core. Fact 16. A teaspoon of neutron star material weighs billions of tons. Imagine holding a teaspoon. It's small, light, harmless. Now imagine filling it with the matter of a neutron star. That same spoon would suddenly weigh as much as a mountain. Billions of tons compressed into a space small enough to fit in your hand. This is the result of unimaginable compression. Inside a neutron star, the atoms that once made up the star's core are crushed together until there are no spaces left between them. Protons and electrons merge into neutrons, creating a kind of matter that no longer behaves like anything we know on Earth. The result is a density so extreme that a cubic centimetre, smaller than a sugar cube, could outweigh every skyscraper in a major city combined. If you could somehow scoop that teaspoon out, it wouldn't stay solid. Freed from the neutron star's enormous gravity, the material would explode outward instantly, releasing enough energy to vaporize everything nearby. It's a form of matter that cannot exist anywhere else, stable only under the crushing pressure of a collapsed star's heart. This single comparison, 1 teaspoon equal to a mountain, reminds us of how strange and powerful the universe truly is. In the quiet of space, density becomes destiny. What was once a shining sun has been folded into a near-perfect knot of matter. Every neutron star is proof that the cosmos can take the vast and make it small, the light and make it heavy, the impossible and make it real. Fact 17. The crust. Harder than any known metal. Beneath the thin glow of a neutron star's surface lies a crust unlike anything we've ever touched. It's not rock, not metal, not even crystal. It's something far beyond all of them, a lattice of atomic nuclei pressed together so tightly that it's stronger than any material known. Scientists estimate that the crust of a neutron star is about 10 billion times harder than steel. The atoms are arranged in near-perfect order, held together by pressures that can crush entire planets. Even the slightest crack in this crust can release energy equivalent to massive earthquakes, what astronomers call starquakes. These quakes can cause the entire star to jolt, suddenly changing its rotation speed. The crust isn't uniform. The outer layer is made of dense atomic nuclei surrounded by a sea of electrons. Deeper down, the nuclei start to melt into strange shapes, rods, sheets and tunnels of nuclear matter that researchers have nicknamed nuclear pasta because of their unusual geometries. Each layer supports the next, forming a kind of cosmic armour. It's this incredible crust that lets neutron stars keep their shape, resisting further collapse. It's humbling to think that beneath a surface no thicker than a few kilometres lies strength beyond imagination, a natural material that could never be forged, only born from the weight of a dying sun. Fact 18. the incredible density that defies imagination. When we talk about density, it's easy to lose perspective. Water weighs 1,000 kilograms per cubic meter. Iron is about 8 times denser. But neutron star matter, around a quadrillion times denser than water. At that density, a single thimbleful would outweigh Mount Everest. The matter is so compact that normal physical intuition simply breaks. There are no gaps between particles. The atoms themselves have collapsed. What remains is a vast ocean of neutrons squeezed into a volume smaller than a city. This density doesn't just make neutron stars heavy, it makes them bizarre. Their gravity bends light, slows time, and warps space around them. If you could somehow stand on the surface, which you can't, you'd be crushed instantly. A single jump would never fall back down. You'd orbit the star instead. Every property of neutron stars comes from this unimaginable density. Their strong magnetic fields, rapid rotation, and gravitational pull. They are the ultimate expression of matter under pressure, the point where the familiar laws of chemistry and physics begin to dissolve into something new. The universe loves extremes, and a neutron star is one of its masterpieces, a monument to how far reality can be stretched before it breaks. Fact 19. The structure, crust, mantle, and core. Though they are tiny by cosmic standards, neutron stars have layers as complex as planets. Scientists divide them into 3 main parts: the crust, the mantle, and the core, each one stranger than the last. The crust is the outer shell, a few kilometers thick, made of superdense atomic nuclei and free electrons. Beneath that lies the mantle, where pressure forces protons and neutrons into exotic shapes, sheets, rods, and tangled networks that make up the nuclear paster region. Deeper still is the core, the heart of the neutron star. Here, the density becomes so high that individual neutrons begin to merge into a fluid. Some theories suggest the very center might contain quark matter, the most fundamental particles in existence, usually confined inside protons and neutrons, now set free by gravity's grip. Each layer plays a role in maintaining balance. The crust provides rigidity, the mantle stores elastic energy, and the core anchors the entire structure. Together they form one of the most stable and fascinating objects ever discovered, the closest thing nature has to a perfect sphere. When we imagine neutron stars, it's easy to think of them as simple, just small, dense remnants. But inside, they are intricate worlds of matter pushed to its absolute limit, layered like the thoughts of a universe still learning what it can become. Fact 20. Why they don't collapse further. Given their mass and gravity, it's natural to wonder why neutron stars don't simply collapse into black holes. After all, they're already unimaginably dense. Why not go one step further? The answer lies in a delicate balance of forces. Gravity is pulling inward with enormous strength, trying to crush the star into a single point. But inside the star, the neutrons resist. This resistance comes from quantum pressure, a fundamental rule of nature that says 2 neutrons cannot occupy the same exact state at the same time. This degeneracy pressure acts like an invisible spring pushing back against gravity's pull. As long as the star's mass remains below a certain limit, about 2 to 3 times the mass of the Sun, this quantum pressure is enough to hold it up. But if it gains more mass, perhaps by absorbing material from a companion star, the balance breaks. The neutrons can no longer resist, and the collapse continues until even light cannot escape, forming a black hole. So neutron stars exist right on the edge between being and vanishing, between matter and pure gravity. They are the universe's tightrope walkers, balanced perfectly between collapse and survival. Their very existence is a quiet miracle of physics, proof that the same laws that allow atoms to exist also keep stars from falling forever. Fact 21. The balance between neutrons and quantum forces. In the heart of a neutron star, balance is everything. Gravity presses inward with unimaginable strength, strong enough to crush mountains into atoms and atoms into dust. Yet the star doesn't collapse. Something invisible pushes back. This quiet resistance comes from the laws of quantum mechanics, a rule that says no two neutrons can occupy the same state at the same time. It's called degeneracy pressure, and it acts like an unseen lattice that holds the universe together when gravity tries to pull it apart. Every neutron in the star is locked in a kind of silent dance, pressed against its neighbours, yet refusing to overlap. The result is a fragile piece, a structure sustained not by walls or matter, but by the principles of physics themselves. In this balance, gravity and quantum pressure become eternal rivals, one trying to compress, the other to preserve. Neither truly wins, they simply coexist, holding the star steady at the very edge of what's possible. It's strange to think that such enormous stability comes not from strength, but from limitation, from the quiet rule that says, enough, no closer. The entire star depends on this whisper of resistance, the same quantum forces that keep the atoms in your own body from collapsing. In the silence of space, this balance becomes a kind of cosmic heartbeat, unseen but always there, keeping the impossible intact. Fact. 22. How neutrons pack together like atomic bricks. Deep inside a neutron star, matter has lost its familiar form. There are no atoms, no electrons swirling in orbits, only neutrons packed together so tightly they behave like the bricks of a universe built under infinite pressure. Imagine stacking spheres until there's no space left between them. That's what happens here. Except these aren't ordinary spheres. They are subatomic particles squeezed into a crystalline grid by forces billions of times stronger than anything found on Earth. This arrangement gives the star its extraordinary density and strength. Each neutron supports its neighbours, passing along the weight of an entire sun. It's like a city made of invisible stone, so compact that a single teaspoon would outweigh all the ships ever built by humanity. The deeper you go, the stranger it becomes. Neutrons may start to merge into exotic forms, hyperons, or even a fluid sea of quarks. Yet even here, some structure remains. The particles align, shift, and adjust, forming patterns that could rival the precision of the finest crystal. If you could somehow see it, this lattice of matter at the brink of collapse, it would look serene, flawless, and impossible. Each neutron locked in its place, holding up the weight of a fallen star, like the bones of a cosmic cathedral built from the ruins of light. Fact 23. The smallest, yet densest stars in existence. In the vast theatre of the cosmos, neutron stars play a paradoxical role. They are among the smallest objects we know, yet among the most massive. A typical neutron star is only about 20 kilometers wide, barely the size of a city. But within that tiny sphere lies more mass than the sun itself. It's as if the universe decided to compress an entire world into something you could walk across in an afternoon. Though no one ever could. The gravity is so intense that even a grain of sand on its surface would weigh millions of tons. These stars are the densest stable objects known, second only to black holes. But unlike black holes, they still have a surface, a boundary where matter resists total collapse. This is what makes neutron stars so mysterious. They are the final moment before the universe gives up its shape entirely. When you look at the night sky, every bright star you see could one day become one of these tiny giants, the smallest, yet the densest of all. They remind us that greatness doesn't always come from size. Sometimes it comes from compression, from what remains when all the unnecessary parts are stripped away. Fact 24. Why they don't shine like normal stars. Normal stars glow because they burn. Their light comes from nuclear fusion, hydrogen fusing into helium in a continuous brilliant fire. But neutron stars are the ghosts of that fire. Their fuel is gone. Their light comes not from burning, but from the memory of heat that once was. When a massive star collapses, its core becomes a neutron star, incredibly hot at first, glowing with leftover energy from the explosion that birthed it. Over time it cools, its brightness fading into a faint, steady glow. Instead of flames, it shines with residual heat and strange radiation, mostly X-rays, invisible to human eyes. Some spin rapidly, creating pulses of light that sweep across the sky like cosmic lighthouses. These are pulsars, neutron stars that seem to blink with an eerie rhythm, the heartbeat of a star long gone. They don't shine in the way we think of stars because their story is different. They are not beginnings, but afterlives, remnants still whispering light long after the fire has gone out. Their glow is not warmth, but memory. A final reminder that even endings can be beautiful if you know how to look. Fact 25. Their faint light and ghostly glow. From a distance, a neutron star might look like a quiet ember floating in space, a small dim point barely visible against the dark. But approach it, in theory, and you'd see something hauntingly beautiful. Its surface, heated to over 1,000,000 degrees, shines not in visible light, but in high-energy radiation, X-rays and gamma rays invisible to our eyes. Through a telescope, it appears as a pale shimmer, a ghostly glow against the black canvas of the universe. Some neutron stars pulse rhythmically as they spin, their magnetic fields channeling beams of radiation that sweep through space like turning searchlights. Others remain silent, cooling slowly through the centuries, their light fading ever so gently. They are not the radiant stars of storybooks. They are the quiet ones, the remnants, the echoes. Their light doesn't dazzle, it hums. It's the soft breath of something ancient that refuses to vanish completely. Each ghostly shimmer you might see through a telescope is a reminder that, even when brilliance fades, traces of it linger, glowing faintly at the edge of forever. In their silence, neutron stars offer one final truth, that even the faintest light can still outlast time. Fact 26. How neutron stars keep spinning. When a star collapses, it doesn't just fall inward, it begins to spin. Like a dancer pulling in their arms, its rotation speeds up as its size shrinks. What was once a sun turning slowly in space becomes a neutron star spinning many times each second. This happens because of angular momentum, one of the quiet laws that keeps the universe in balance. When the massive outer layers of a dying star explode away in a supernova, the core that remains must conserve its spin. But since that core is now thousands of times smaller, it rotates thousands of times faster. Some neutron stars whirl at dizzying speeds, hundreds of revolutions per second. Their surfaces move faster than the speed of sound, each rotation marking another beat in the universe's silent rhythm. And yet, even in this furious motion, there is grace. The spin doesn't slow easily. The star's density and magnetic field help preserve its rotation for millions of years. Over time, it gradually loses energy, its speed softening like a slowing clock, but never truly stopping. Each spinning neutron star is like a cosmic timekeeper, a memory of the day a giant star collapsed, still turning endlessly through the dark. Its motion is the remnant of an ancient dance, one that began in fire and continues in silence. Fact 27. The role of magnetic fields in shaping them. If gravity gives a neutron star its strength, then magnetism gives it personality. When the star collapses, its magnetic field is squeezed along with its mass, becoming billions of times stronger. The result is a magnetic field so intense it can twist light, bend charged particles, and shape the space around it. These magnetic fields act like invisible sculptors. They control how the star radiates, where its beams of energy are released, and even how it spins over time. They can trap particles in loops that circle the star, glowing in high-energy arcs. In some neutron stars, these magnetic fields become so strong they defy comprehension. reaching trillions of times the strength of Earth's. Such stars are called magnetars, and their fields are so powerful they can tear atoms apart from thousands of kilometers away. These forces also give rise to the star's pulses, streams of radiation that sweep through space as the star spins. Each flash we detect from a pulsar is really a brush of these magnetic beams crossing our line of sight, like the turning of a cosmic lighthouse. In every way, the magnetic field defines the neutron star's identity. It decides how it glows, how it evolves, and how it communicates with the universe. It's a reminder that even in silence, invisible forces are still painting the cosmos with motion and light. Fact 28. Why some rotate. Hundreds of times per second. Some neutron stars spin with astonishing speed, hundreds, even over 1,000 rotations every second. These are called millisecond pulsars, and their speed is almost beyond imagination. How can something so dense, so massive, move that fast? The answer lies in what happens long after their birth. Many neutron stars exist in pairs, orbiting another star. Over time, they draw in matter from their companion, a process called accretion. As the material spirals down onto the neutron star, it transfers angular momentum, spinning it faster and faster. The process is like winding a cosmic toy top. Each drop of falling matter adds a little more spin, until the neutron star becomes one of the fastest rotators in the universe. At these speeds, the surface moves at a significant fraction of the speed of light. Yet the star doesn't fly apart. Its gravity is too strong. The balance holds, and the star continues to whirl in perfect rhythm, sending out pulses of radiation like a heartbeat you can only detect through radio waves. Every millisecond pulsar is a monument to endurance, a survivor reborn through motion. Even after death, it keeps spinning, turning collapse into rhythm and silence into song. Fact 29. The mysterious magnetic poles. A neutron star's magnetic poles are unlike anything on Earth. They're regions where the star's immense magnetic field concentrates, channeling energy into narrow beams of radiation. These poles are often misaligned with the star's spin axis, so as the star rotates, these beams sweep across the sky like twin cosmic searchlights. When one of these beams crosses Earth, we see a pulse, a blink of light that repeats with perfect regularity. That's why neutron stars were first mistaken for signs of intelligence when they were discovered. The timing was so precise it seemed almost deliberate. But the truth was even more extraordinary. The regular rhythm came from nature itself, a star's magnetic heartbeat made visible across light years of space. Around these poles, the magnetic fields can twist plasma into spirals, accelerate particles to near light speed, and create bursts of radiation that flash across the galaxy. Some poles are so active they can shift the star's rotation, slightly changing its timing with each eruption. Even now, we don't fully understand how these poles evolve, or why they're so perfectly aligned in some stars but chaotic in others. But their mystery makes them beautiful. Proof that even the most precise rhythms of the universe come from wild, unpredictable beginnings. Fact 30. The thin atmosphere surrounding a neutron star. Though they are small and dense beyond belief, neutron stars still wear a thin veil, a whisper of atmosphere clinging to their surfaces. It's only a few centimeters thick, made mostly of hydrogen, helium, and sometimes heavier elements. Yet within that shallow layer, temperatures can reach over 1,000,000 degrees. This atmosphere glows faintly with X-rays, giving the neutron star its soft ghostly light. It also bends light in strange ways, because the star's gravity is so strong that photons, particles of light, curve as they escape. If you could stand above it, which no one could, you'd see something surreal. The entire surface of the star visible at once, bent upward by the warping of space. The atmosphere would shimmer like a liquid flame, dense, hot, and always moving. The gases here are so compressed they no longer behave like air, but like plasma. A glowing sea of charged particles swirling over a crust stronger than steel. Though it's barely there, this atmosphere tells the story of what remains after a star's final collapse. The faint echo of what was once a sun, still clinging to its surface, refusing to fade entirely. Even the thinnest layer of matter can carry history. Around a neutron star, that history glows softly, forever suspended between fire and silence. Fact 31. What makes a neutron star a pulsar? Not every neutron star becomes a pulsar. What makes a neutron star transform into one of these cosmic lighthouses is a combination of rotation and magnetism. When the star spins rapidly and has a strong magnetic field, beams of electromagnetic radiation are focused along its magnetic poles. Because these poles are often tilted relative to the star's rotation, the beams sweep across space like a lighthouse over an ocean. If Earth happens to lie in the path of one of these beams, we see it flash. A pulsar. The rhythm is astonishingly precise. Each pulse is timed by the neutron star's rotation, sometimes to better accuracy than the most precise clocks on Earth. The star itself is unchanged, yet the way it interacts with space and light makes it a brilliant moving signal, a celestial metronome marking time across the galaxy. Every pulsar reminds us that motion and magnetism, when combined under extreme conditions, can turn a quiet, dense remnant into a glowing beacon, an object that seems alive with rhythm and purpose, even across the vast distances of space. Fact 32. The Discovery of Pulsars by Jocelyn Bell Burnell. In 1967, a young scientist named Jocelyn Bell Burnell was listening to the universe through a radio telescope. Night after night, her instruments traced invisible waves across sheets of paper. Then she noticed something unusual, a tiny regular pulse, repeating with perfect precision. At first it seemed impossible. Could it be interference? A satellite? The paper kept blinking with the same rhythm. They jokingly called it LGM-1, Little Green Men, because no known star could produce such a steady signal. Soon more pulses appeared in other parts of the sky. The team realized that these were not messages but spinning neutron stars, their magnetic beams sweeping past Earth like clockwork. Pulsars were born as a new class of celestial object, and the discovery reshaped astrophysics forever. Jocelyn Bell Burnell had uncovered not just a star but a rhythm, a heartbeat of the cosmos pulsing steadily across light years, connecting distant points of the galaxy through silent, unwavering time. Fact 33. The rhythmic beacons of the universe. A pulsar is like a lighthouse in the dark, sweeping beams of radiation across the emptiness of space. Its pulses arrive with astonishing regularity, sometimes hundreds of times per second, turning the invisible into something we can measure, watch, and admire. These rhythmic beacons guide astronomers, helping map the galaxy and test the limits of physics. Each pulse is a story, the frozen memory of a star's collapse, the spin preserved over millions of years, the magnetic field channeling energy in perfect lines. The universe is vast and mostly silent, but pulsars are its steady drumbeat. They mark time in the galaxy and remind us that even in darkness there is order, pattern, and beauty. To see a pulsar is to witness a pulse older than humanity, a rhythm that began in fire and continues through eternity, gently beating across the cosmos. Fact 34. Why pulsars blink with perfect timing. Pulsars appear to blink because of their rapid rotation combined with tilted magnetic poles. As the star spins, its beams sweep past like the arm of a lighthouse. From our point of view on Earth, the beam crosses our line of sight at precise intervals. The timing is so perfect that even the slightest changes, caused by gravitational interactions or tiny shifts in the star's rotation, can be measured. Some pulsars are so regular that astronomers use them as cosmic clocks, keeping time with better accuracy than atomic clocks. This precision comes from the neutron star's rigidity and density. Its compact core resists wobbling or distortion, preserving the pulse over millions of years. The star may spin hundreds of times per second, yet each pulse arrives like clockwork, a quiet testament to the power of structure under extreme conditions. The blink is not just light, it's a heartbeat, a signal from the universe that the rhythm of creation endures, even in objects born of death. Fact 35. How fast they spin. Some faster than a blender. Some pulsars spin so quickly it boggles the mind. While most rotate a few times per second, millisecond pulsars can whirl hundreds of times each second. Imagine a neutron star spinning faster than the blades of a kitchen blender, yet holding together perfectly under forces that would tear any normal object apart. This incredible rotation is fueled by a combination of the star's original angular momentum and sometimes by matter falling in from a companion star, spinning it up like winding a cosmic top. The faster a pulsar spins, the more extraordinary its beams of radiation become. Each pulse becomes a flash, slicing through space like a cosmic metronome. Even at these speeds, the star remains stable, its mass and quantum forces holding it together in a delicate, eternal balance. These spinning wonders remind us that the universe is capable of extremes beyond imagination, and that even in small, city-sized remnants, there can be power, speed, and beauty beyond anything on Earth. Fact 36. Millisecond pulsars and their extreme rotation. Some neutron stars spin so fast, they seem almost impossible. These are millisecond pulsars, rotating hundreds of times per second. To imagine it, picture a star no wider than a city spinning faster than the blades of a blender, yet holding together perfectly under forces that would shatter anything else. How do they achieve such dizzying speeds? Often, it's thanks to a companion star. Over time, material flows from the companion onto the neutron star, transferring angular momentum and spinning it faster and faster. Each bit of infalling matter acts like a gentle push on a cosmic swing, accelerating the star's rotation without breaking it. Despite this incredible motion, millisecond pulsars remain remarkably stable. Their rotations are precise, almost unchanging, making them some of the most reliable clocks in the universe. These stars carry the memory of the collapse that created them, yet their spinning is a new story, one of endurance, refinement, and extraordinary rhythm. Millisecond pulsars are reminders that even the smallest objects, when born under extreme conditions, can harbour motion that stretches imagination. Their spin is a song of physics, played at a speed the human mind can barely comprehend. Fact 37. How pulsars help scientists measure time in space. Pulsars are not just beautiful, they're astonishingly useful. Their pulses arrive with incredible regularity, so precise that astronomers use them as cosmic clocks. Some millisecond pulsars keep time more accurately than the best atomic clocks on Earth. By observing these pulses, scientists can measure distances in space, detect the subtle bending of light by gravity, and even sense ripples in space-time known as gravitational waves. Each pulse acts like a heartbeat of the galaxy, a signal that persists for millions of years, cutting through the dark with unwavering rhythm. Pulsars allow us to track the motion of stars, test the limits of physics, and explore corners of the universe we cannot visit. Their precision is a gift, the universe itself providing a timepiece. Steady and unchanging, reminding us that order exists even among the extremes of matter and energy. It's almost poetic, the remnants of dying stars teaching us about time, space, and the hidden rhythms of the cosmos. Every pulse is a tiny whisper of the universe's ongoing story. Fact 38. Magnetars. Neutron stars on magnetic steroids. Among neutron stars, magnetars are the true heavyweights. Their magnetic fields are trillions of times stronger than Earth's, bending particles, light, and sometimes even the very fabric of space. Imagine a star with the density of a city but with a force field so powerful it could distort a planet from thousands of kilometers away. Magnetars are born like other neutron stars, but their magnetic fields are amplified during collapse. These fields twist and coil with invisible energy, making the star prone to sudden bursts, violent flares that release more energy in a fraction of a second than the sun produces in 100,000 years. Despite their power, magnetars are tiny, city-sized beacons of extreme physics. Their very existence challenges our understanding of what matter can endure, what forces can coexist, and how the universe can concentrate such energy into a single, small object. They are the ultimate expression of intensity, showing that even in the quiet aftermath of stellar death, the cosmos can store forces beyond imagination, ready to flare, twist, and shine with sudden brilliance. Fact 39. The most powerful magnetic fields ever recorded. Magnetars hold the record for the strongest magnetic fields in the universe. While Earth's field is enough to guide a compass, a magnetar's field is so intense it can strip electrons from atoms from thousands of kilometers away. These magnetic fields shape everything around the star. They control the flow of charged particles, sculpt the emission of radiation, and create bursts that ripple through space. Near a magnetar, ordinary physics begins to warp. Light bends, energy behaves strangely, and even space itself feels the tug of this invisible power. The magnetic field is the star's signature, its invisible aura. Unlike visible light, you cannot see it directly, but you can sense its effects. It's a reminder that in the universe, some of the most powerful forces are unseen, yet they shape everything we can observe. Magnetars are proof that even in a tiny dense sphere, nature can store energy beyond imagination, a reminder that extremes exist, waiting to surprise us. Fact 40. How magnetars can twist space itself. Magnetars do more than just shine or flare. They can warp the very fabric of space around them. Their extreme magnetic fields distort particles and photons, bending light and energy in ways that seem almost magical. Near a magnetar, space behaves strangely. The polarization of light shifts, radiation is redirected, and particles accelerate along twisted magnetic lines. Scientists can observe these effects across light years, seeing the invisible influence of a star so small, yet so powerful, that it dominates its surroundings. Despite their violence, magnetars are silent from a distance, glowing faintly when inactive, but when their magnetic energy is released suddenly, they erupt in flares that ripple across the galaxy. Space itself seems to shiver under their influence, a reminder that even empty space is not empty, and even the smallest stars can command incredible power. Magnetars show us that the universe is not always calm, that energy can be concentrated, twisted, and released in ways that defy ordinary understanding. They're extreme, mysterious, and beautiful, cosmic reminders that power can exist in silence, waiting for the perfect moment to shine. Fact 41. What happens when a magnetar releases energy? Magnetars are like cosmic pressure cookers, storing unimaginable energy in their magnetic fields. Occasionally that energy escapes in a sudden violent release. In a fraction of a second, the star erupts with a flare so intense it can outshine every star in its galaxy combined. During this release, particles are accelerated to near the speed of light, radiation streams outward in all directions, and space itself seems to ripple under the force. The flare doesn't destroy the magnetar, the star remains intact, but the event reshapes its surroundings, influencing nearby gas, dust, and even the paths of light passing close by. These eruptions are rare, unpredictable, and extraordinary. From our vantage point across the universe, we see only a brief flash, a fleeting pulse of raw cosmic power. Yet each release is a reminder that even a small city-sized object can hold energy beyond comprehension, waiting silently until the moment it decides to speak. Fact 42. Giant flares that outshine entire galaxies. A magnetar flare is the universe's equivalent of a cosmic spotlight. In seconds, it can release more energy than our sun emits in 100,000 years. The light travels across the galaxy, illuminating everything it touches with a brief dazzling brilliance. These flares are invisible to our eyes. Most shine in X-rays or gamma rays, yet they are detected by instruments sensitive enough to trace their paths across millions of light years. They flare, pulse, and fade, leaving behind only a whisper of their passing power. It's awe-inspiring to think that a star smaller than a city can, for a moment, rival the glow of billions of other stars combined. These flares show the extremes of physics in action, the results of matter and magnetism pushed beyond imagination. In their brilliance, magnetars remind us that the universe is not only vast, but also capable of sudden, stunning displays, a reminder that even the smallest objects can hold the power to illuminate the cosmos. Fact 43. The strange noises. Magnetars. Make in radio waves. Magnetars are not quiet. While most of their energy is invisible, some emits in radio waves. When this happens, telescopes can listen to the strange signals, bursts and pulses that sound almost like whispers from the edge of space. These radio bursts are irregular, unlike the rhythmic pulses of normal pulsars. Sometimes they appear in short, sharp flashes. Other times they linger in longer waves. Scientists are still unraveling what creates these signals, but they may arise from interactions between the magnetar's magnetic field and its outer layers of plasma. Listening to a magnetar is like hearing the heartbeat of a star under immense pressure. The sound isn't audible in the human sense, but in a converted signal, it becomes an eerie, hypnotic pattern, a reminder that even in silence, energy is always in motion, always alive. Fact 44. The link between magnetars and mysterious fast radio bursts. Some of the universe's most baffling phenomena, fast radio bursts, FRBs, may be linked to magnetars. FRBs are sudden flashes of radio waves, lasting only milliseconds, yet they carry more energy than the sun emits in a day. Magnetars, with their magnetic storms and flares, are prime candidates for these bursts. When a magnetic flare erupts, it can send ripples through the star's outer layers, generating a pulse of radio waves that travels across billions of light years to reach Earth. The connection is still being studied, but each observation brings us closer to understanding these fleeting cosmic mysteries. It's as if the universe occasionally speaks in a secret language, one that only the most patient and attentive listeners can decode. Fact 45. Why magnetars? May one day explain cosmic mysteries. Magnetars hold keys to questions we have barely begun to ask. Their extreme density, energy and magnetic fields push the boundaries of physics, offering insights into how matter behaves under unimaginable pressure. By studying magnetars, scientists hope to understand fast radio bursts, the nature of magnetic fields, and even the fundamental structure of matter itself. Each flare, each pulse, each subtle shift in energy becomes a clue, a whisper from a star that has survived collapse, holding secrets in its tiny, dense core. These stars show that the universe still holds mysteries that are not only vast but accessible. If we listen carefully, with the right tools and patience, magnetars may illuminate questions about the cosmos we have yet to even imagine. Even in their quiet moments, they teach us something profound, that the universe preserves its secrets in small, dense objects, and that sometimes the greatest mysteries come from the tiniest, most extreme stars. Fact 46. The outer crust made of iron and nickel. The outer layer of a neutron star is surprisingly familiar, made mostly of iron and nickel, elements we recognize from Earth, from stardust, and from our own bodies. Yet here, under extreme gravity, these metals behave in extraordinary ways. The crust is thin, just a kilometre or so deep, but incredibly strong, billions of times harder than any material we know. It supports the star's mass like a delicate shell holding a colossal secret. Each atom is pressed together with such force that the crust can survive the twisting and spinning of the star for millions of years. From a distance, the outer crust is invisible, hidden beneath a faint glow. Yet it is the first layer to meet space, a protective skin that holds in the immense pressure and energy below. In a way, it's a gentle reminder that even the most extreme objects in the universe still have a surface, a boundary, a quiet layer that touches the cosmos delicately. The outer crust is where familiar matter meets the unimaginable, a bridge between the world we know and the mysteries that lie at the star's core. Fact 47. The inner crust. Where neutrons begin to drip beneath the iron-rich crust, the pressure grows even more intense. Here lies the inner crust, a strange realm where neutrons begin to escape from nuclei, forming a fluid sea amidst the remaining atomic lattice. This is the first place inside the star where matter behaves unlike anything on Earth. The neutrons are free-flowing, yet trapped, moving through a solid network like water seeping through frozen rock. The crust flexes slightly under stress, sometimes producing starquakes, tiny shifts that send ripples across the star. It's a delicate balance. Gravity pushes inward, the nuclear lattice pushes outward, and the neutrons move between the two, creating a surreal landscape of dense, half-fluid matter. The inner crust shows us that in extreme conditions, matter refuses to act as expected. It adapts, finds patterns, and survives. It is a quiet, restless frontier, a place of transition between the familiar and the truly alien. Fact 48. The core. Where matter becomes nearly incomprehensible, deeper still lies the core, the heart of the neutron star. Here, density reaches mind-bending extremes. A single teaspoon of this matter would weigh billions of tons. The familiar laws of matter begin to stretch. Atoms are crushed, electrons merge with protons to form neutrons, and nuclei themselves vanish. The core is a place where the imagination struggles to keep pace with reality. It is almost incomprehensible, matter packed so tightly that every cubic centimetre is a universe unto itself. Scientists cannot observe it directly. They must infer its properties through pulsations, magnetic fields, and the star's gravitational behaviour. Yet even from afar, the core whispers its secrets, extreme, dense, and enduring. It is a reminder that the universe is vast not only in space, but in the forms matter can take, and that even in silence, these tiny stars hold unimaginable complexity. Fact 49. Theories about quark matter. Some scientists believe that at the very centre, the neutrons themselves may dissolve into a quark-gluon plasma, a soup of fundamental particles called quarks. This is matter in a form we cannot recreate on Earth, a primordial state that existed only in the first moments after the Big Bang. In this view, the neutron star becomes a laboratory of the universe, a city-sized container of matter at its most extreme. Quarks move freely in this dense core, creating forces and pressures that are both strange and beautiful. We cannot see it, but we can imagine it. A dense, shimmering ocean of particles, each dancing under rules so different from what we know that it feels almost magical. Quark matter is not just theory. It's a possibility that reminds us that even a single star can contain physics still waiting to be discovered. Fact 50. Could the core contain strange matter? Even more speculative is the idea that the core might host strange matter, a type of quark matter containing strange quarks. This exotic substance would be stable under the star's extreme pressures, potentially forming a kind of self-contained universe inside a city-sized star. If true, Neutron stars would not just be remnants of collapsed stars, they would be containers of a fundamentally new state of matter, holding secrets about the building blocks of reality. Strange matter, if it exists, would subtly influence the star's rotation, its magnetic field, and its behavior during collisions with other stars. Every pulse, every flare, every millisecond of spin could carry hints of this mysterious substance, waiting for astronomers to decode. It's a reminder that even in objects we can barely imagine, the universe continues to experiment, revealing new possibilities hidden within the dense hearts of stars. Fact 51. The pressure inside. Trillions of times. Earth's inside a neutron star, pressure reaches levels that are almost impossible to imagine. Every cubic centimetre is squeezed with a force trillions of times stronger than the weight of Earth itself. Atoms are crushed, electrons merge with protons, and neutrons are packed shoulder to shoulder in a dance of quantum resistance. This pressure is what keeps the star from collapsing into a black hole. Gravity pulls inward relentlessly, yet quantum forces and the rigidity of matter push back, holding the tiny sphere together. The balance is delicate and eternal, maintained over millions of years in silence. If we could somehow visit this interior, which we cannot, we would see matter behaving in ways that defy intuition. A teaspoon of neutron star material would outweigh all human civilization. It is a realm where the ordinary becomes extraordinary, and the universe whispers its secrets through forces too immense to touch. Fact 52. The temperature right after formation. When a neutron star is first born, it is unimaginably hot. Temperatures soar to hundreds of billions of degrees, rivaling the heart of the supernova that created it. At first, it glows in X-rays and gamma rays, a furnace of energy compacted into a city-sized sphere. This heat is the remnant of the star's collapse, the last echo of a supernova's fury. In these early moments, the star emits vast amounts of energy, warming its surroundings and sending particles spinning through space at incredible speeds. Despite its tiny size, the newborn neutron star is a cosmic furnace, radiating energy in a way that makes its very existence both fragile and magnificent. The heat slowly fades over centuries, but the memory of that inferno remains, embedded in the star's structure and its ghostly glow. Fact 53. How they slowly cool. Over time, after the initial blaze, neutron stars begin a slow, patient cooling. Heat radiates away in X-rays, gradually fading into the cold silence of space. The outer layers cool first, while the dense core retains warmth for millions of years. This cooling is not uniform. Different layers lose heat at different rates, and the processes inside the star, from neutrino emission to superfluid behavior, create a gentle, almost rhythmic transition from searing fire to quiet ember. As the star cools, its glow becomes fainter, but the processes inside continue, hidden from view, a slow, majestic dance of energy and matter. Even in cooling, the neutron star is alive in its own quiet, eternal way. Fact 54. The superfluid layers. Inside the neutron star, matter behaves in ways that seem almost magical. Some layers become superfluids, liquids that flow without friction. Neutrons glide through this inner sea, moving effortlessly, as if the star itself is breathing softly. Superfluidity allows the star to transfer heat, rotate smoothly, and respond to internal stresses in unusual ways. It also contributes to the star's stability, allowing it to survive enormous forces without cracking or collapsing. It is a state of matter that exists only under extreme conditions, a silent miracle of physics that transforms the interior into a realm both delicate and unbreakable. Fact 55. Why the core may act. Like a single quantum fluid. Deep in the core, the neutrons may act collectively, forming a single quantum fluid. In this state, particles lose their individuality, moving in harmony as a coherent whole. the star becomes more than the sum of its parts, a single entity obeying the strange and beautiful rules of quantum mechanics. This unified behavior affects rotation, magnetic fields, and the way the star reacts to stress. The core, though invisible to us, hums with the subtle rhythm of quantum order. It's as if the universe has orchestrated an entire star to behave like a single, flowing entity, a cosmic symphony of density, motion, and energy. In this way, the neutron star is both a laboratory and a work of art, a city-sized object where matter reaches the edge of comprehension, and yet continues to move with grace and elegance. Fact 56. The possibility of superconductivity. Inside, deep within a neutron star, the extraordinary pressure and density create conditions unlike anything on Earth. Some scientists believe that parts of the interior may become superconductors, regions where electricity flows without resistance. In this strange environment, currents move effortlessly, circulating for millions of years. Magnetic fields are guided along these invisible pathways, twisting and shaping the star's behavior. Superconductivity inside a neutron star is a silent conductor, orchestrating the flow of energy in ways we can detect but never touch. It's a reminder that even in the smallest, densest objects in the universe, nature finds ways to create order, efficiency, and harmony. The star, in its quiet existence, is a laboratory of cosmic wonder, performing physics far beyond human experience. Fact 57. The quantum dance of particles under pressure. Inside a neutron star, particles no longer behave individually. Neutrons, protons, and electrons are packed so tightly that they interact in a complex quantum dance. They move together in coordinated patterns, guided by the subtle rules of quantum mechanics, creating layers of matter that flow, twist, and resist collapse. These microscopic interactions determine the star's rotation, heat distribution, and magnetic field. Even a small shift in this quantum choreography can ripple outward, affecting the star's behavior for millennia. It's a dance that cannot be seen with the eye, yet its effects reach across the galaxy, whispering secrets through pulses, flares, and gravitational waves. The quantum world of a neutron star is a reminder that the universe's smallest components can shape the grandest structures. Fact 58. How gravity keeps everything locked. In gravity is the invisible hand that holds a neutron star together. Every particle, every layer, every neutron is locked in place by a force so strong it dwarfs anything we experience on Earth. This is what prevents the star from collapsing into nothingness or tearing itself apart as it spins. Gravity also shapes the star's structure, squeezing matter into layers, compressing nuclei, and creating conditions where quantum effects dominate. Without this relentless pull, none of the delicate balances inside the star could exist. It is gravity's quiet, persistent presence that allows the neutron star to survive for millions of years, a silent guardian that binds matter, energy, and magnetism into a small, dense, enduring sphere. Fact 59. The mystery of what lies at the very centre. At the very heart of a neutron star lies the unknown. Scientists cannot see it directly, yet every observation hints at astonishing possibilities. Could it be a sea of quark matter? Strange matter? Something entirely new? A form of matter that has never existed in our laboratories? The centre is a cosmic secret, compressed to extremes that challenge human understanding. Each pulsation, flare, and subtle shift is a clue, a whisper from a realm where matter behaves unlike anything we know. It's a reminder that even objects as studied as neutron stars still hold mysteries, waiting for curious minds to explore them, gently revealing the universe's infinite complexity. Fact 60. Why even? Supercomputers can't model them perfectly. Despite advances in physics and computing, neutron stars remain beyond perfect simulation. Their density, quantum interactions, magnetic fields, and relativistic effects create a system too complex for even the fastest supercomputers to model fully. Every approximation is a glimpse, a map of shadows hinting at the reality. Scientists rely on observations, pulses, flares, gravitational waves, to guide their understanding, piecing together the story of these tiny extreme stars. Even in our age of technology, the universe reminds us that some things are meant to inspire awe. Neutron stars are among them, objects small in size but vast in mystery, challenging our understanding and inviting us to dream about the limits of matter, energy, and imagination. Fact 61. The incredible spin. Speeds after birth. When a neutron star is born, it can spin with unimaginable speed, sometimes hundreds of times per second. Imagine a city-sized object spinning faster than the blades of a kitchen blender, yet holding together perfectly under pressures billions of times stronger than Earth gravity. This incredible rotation comes from the conservation of angular momentum. As the parent star collapses, its outer layers fall inward, and the core spins faster, much like a figure skater pulling in her arms to spin more swiftly. In those first moments, the star is a dizzying whirlwind, glowing in X-rays and gamma rays, a tiny, dense whirlwind carrying the memory of the star that once was. Its spin is a signature of its violent birth, a rhythm that will slowly guide the star's journey through the galaxy for millions of years. Fact 62. Why some neutron stars slow down over time. Even the fastest spinning neutron stars gradually lose speed. Magnetic fields, radiation, and the emission of particles act as subtle brakes, slowing the star's rotation over millennia. This deceleration is quiet and relentless. It is as if the star, having burned with the intensity of youth, begins a gentle, measured aging. Each loss of speed tells a story, of energy radiated into space, of interactions with its surroundings, and of the passage of time in a cosmic landscape where years are counted not by calendars, but by pulses of light. The slowing spin does not weaken the star, it transforms it. A once blindingly fast pulsar becomes a steadier beacon, a calm metronome marking the rhythm of space for distant observers. Fact 63. Glitches, when they suddenly speed up. Sometimes, a neutron star surprises astronomers. After slowly decelerating for centuries, it may suddenly speed up, an event known as a glitch. These glitches are small but significant. In a matter of seconds or minutes, the star's rotation jumps forward, as if it remembers a youthful burst of energy hidden inside. Pulses that were once steady and slow suddenly arrive a fraction of a second earlier, and scientists scramble to understand the cause. Glitches reveal that even in a star that seems eternal and unchanging, motion and energy can shift unexpectedly. The interior of the star is restless, and these subtle shifts remind us that the cosmos is always alive, even in objects that appear frozen and silent. Fact 64. Theories about what causes. These glitches scientists believe glitches may arise from interactions deep inside the neutron star. The superfluid layers of neutrons may suddenly transfer angular momentum to the crust, or star quakes may adjust the structure of the dense shell. Both explanations paint a picture of a star as a living, moving object, a city-sized sphere where forces, quantum effects, and magnetic fields interact in complex, delicate ways. Each glitch is a heartbeat from the interior, a fleeting signal of matter under extreme conditions, and a reminder that even the densest stars are not perfectly rigid. Glitches are cosmic surprises, quiet eruptions from a star's hidden world, letting astronomers glimpse its inner secrets in fleeting pulses. Fact 65. The gradual aging of a pulsar. Over millions of years, a pulsar ages slowly. Its spin slows, its pulses lengthen, and its glow dims in X-rays and gamma rays. Yet even in this quiet phase, the star continues to influence space, emitting radiation, shaping magnetic fields, and sometimes surprising observers with glitches. Aging pulsars are serene sentinels of the galaxy. Their presence is subtle but persistent, a gentle reminder of the life cycles of stars and the passage of time on a cosmic scale. They teach us that even after violent beginnings, quiet endurance can be a form of beauty, a soft pulse marking the rhythm of the universe. Fact 66. How magnetic drag affects their rotation. As neutron stars spin, their magnetic fields act like invisible brakes, slowing them down over time. Charged particles trapped in the star's magnetosphere interact with the field, carrying away energy and gently reducing the star's spin. This process is subtle, yet relentless. The star seems to glide through space, its dizzying rotation gradually softening like a pendulum slowing under friction. Magnetic drag is a quiet conversation between energy and matter, a cosmic reminder that even the universe has rules, subtle forces that guide motion and change. It is not a sudden force, but a patient one, shaping the star's life and slowing its heartbeat without destroying its rhythm. In this quiet dance, the neutron star's rotation becomes a record of its history, a story written in invisible magnetic lines. Fact 67. How they move through space. After birth, neutron stars rarely stay where they are born. The supernova that creates them often sends them hurtling into the galaxy. Their tiny, dense bodies travel through space like cosmic arrows, weaving through the remnants of their former star and interstellar gas. These journeys are quiet and swift. Some move at hundreds of kilometers per second, slipping through the galaxy with almost silent grace. Their paths are influenced by gravity, the interstellar medium, and their own internal dynamics, tracing arcs that will last millions of years. Watching a neutron star travel is like imagining a tiny spinning city drifting through the cosmos, a relic of explosive death moving with calm persistence through the vast emptiness. Fact 68. Some travel millions of kilometers per hour. Some neutron stars are true speedsters. Traveling at millions of kilometers per hour, they escape their birthplaces with staggering velocity. In a human lifetime, they can traverse thousands of light years, leaving the remnants of their supernova far behind. These cosmic sprinters carry the energy of their violent birth into space, a testament to the incredible forces that formed them. Their speed is not random. It reflects the explosion's asymmetry, the star's internal spin, and the interaction of magnetic and gravitational forces. It is a quiet thrill of motion, a reminder that even small, dense stars can move across the galaxy with breathtaking swiftness, a testament to the enduring energy of creation. Fact 69. The kick they get from their supernova. Explosion neutron stars often receive a kick during the supernova that forms them. The explosion is rarely perfectly symmetrical, and this imbalance propels the newborn star at incredible speeds. This kick is tiny in the scale of the explosion but enormous in effect. It sets the star on a new path through the galaxy, sometimes toward interstellar voids, sometimes weaving among other stars. It is a silent nudge from the universe, the star's personal launch into a life of rotation, radiation, and cosmic travel. The kick is also a reminder that even the most violent moments of creation leave traces, subtle yet powerful, echoing through millions of years of motion. Fact 70. Why some fly out of their galaxies. Entirely, in rare cases, neutron stars are kicked so forcefully that they escape the gravitational pull of their galaxies entirely. They drift alone in intergalactic space, spinning silently, glowing faintly, and travelling across the vast emptiness between stars. These rogue stars are lonely travellers, relics of death and creation, reminders that the universe is not bound by human expectations. Even in isolation, they continue their dance of rotation, magnetic fields, and occasional flares, silently shaping the space around them. Flying beyond their galaxies, they become messengers of stellar life, emissaries of creation, and cosmic reminders that energy, motion, and matter never truly rest. They only move, slowly unfolding across the eternal canvas of space. Fact 71. Binary neutron stars. Orbiting each other, some neutron stars are not alone. They exist in binary systems, locked in a gravitational dance with a companion star. These pairs orbit each other with incredible speed, sometimes circling dozens of times per minute. The gravity between them is immense, bending space and twisting the paths of light. From afar, they seem like cosmic dancers, moving in a rhythm dictated by physics and time. Their closeness allows them to exchange energy, interact magnetically, and even distort each other's structure ever so slightly. These stellar partnerships are rare, delicate, and beautiful. Examples of how gravity can choreograph a dance that lasts millions of years, a subtle but eternal rhythm in the quiet of space. Fact 72. How gravitational waves are born from these pairs. As two neutron stars orbit each other, they stir the very fabric of space-time. Their motion sends out ripples called gravitational waves, spreading across the universe like the rings from a pebble tossed into a pond. These waves are faint, yet profound, carrying information about mass, speed, and the nature of gravity itself. When they reach Earth, they are detected as tiny oscillations, imperceptible without instruments designed to feel the subtle pulse of space-time. In a way, these waves are whispers from the cosmos, echoes of an invisible dance between two incredibly dense spinning stars. Each ripple is a story, a heartbeat, a rhythm that reminds us that motion, energy, and gravity are intertwined in ways that are both beautiful and mysterious. Fact 73. The famous collision. Detected in 2017. In 2017, astronomers witnessed a neutron star collision for the first time in human history, known as GWF 7. This event was both a gravitational wave and a light show. For the first time, we observed the cosmic embrace of two neutron stars merging in real time. The collision produced gamma rays, X-rays, and visible light, creating a brilliant cosmic flare called a kilonova. It was a fleeting moment, lasting only days in visibility, yet it revealed secrets hidden for billions of years. How neutron stars interact, how their matter behaves, and how energy spreads across space. This event was a reminder that even tiny stars, no larger than a city, can shape the universe, leaving traces of their final dance for millions to observe. Fact 74. The gold and platinum made from merging neutron stars. One of the most poetic outcomes of neutron star collisions is the creation of heavy elements, including gold and platinum. The immense energy and neutron-rich matter thrown off during a merger allow atomic nuclei to form elements heavier than iron. When we hold a gold coin or admire a platinum ring, we may be touching matter born from ancient stellar collisions, millions or even billions of years ago. The universe, in its quiet cycles of death and creation, recycles stars into treasures, weaving the cosmos into objects we can hold and cherish. It is a reminder that beauty and wealth are cosmic byproducts, forged in violence but delivered in quiet elegance, bridging the universe and human experience. Fact 75. What happens when two neutron stars finally collide? When neutron stars collide, the result is both violent and spectacular. The stars spiral inward, spinning faster and faster until they merge in a flash of light and energy. The collision can produce a black hole, or leave a hypermassive neutron star spinning briefly before collapsing. In the moments of merger, gravitational waves ripple outward, matter is ejected at incredible speeds, and a kilonova lights up the sky. It is a cosmic finale, both destructive and creative, a reminder that endings often birth new beginnings. From afar it appears as a fleeting, beautiful glow. Up close, the forces at work are extreme beyond imagination. Two tiny stars, denser than anything we can replicate, come together and remind the universe, and us, that creation and destruction are intertwined, and that even in the smallest objects there is vast, transformative power. Fact 76. How we detect neutron stars from Earth. Neutron stars are tiny, dense, and distant, yet we can detect them from Earth. They do not shine like ordinary stars, but they leave traces in radiation, in radio waves, X-rays, and gamma rays. Astronomers use these signals like cosmic breadcrumbs, following them across the darkness of space. Each pulse, flare, or flicker is a message from a star thousands or millions of light years away. By carefully observing timing and intensity, scientists can identify neutron stars and even understand their rotation, magnetic fields, and companions. It is a delicate process, like listening for a heartbeat from across a city. The signals are faint, yet persistent, whispering stories of stars that have survived collapse and continue spinning silently through the universe. Fact 77. The importance of radio telescopes. Radio telescopes are our ears to the cosmos. They detect the faint radio waves emitted by pulsars, the spinning, magnetized neutron stars that act like cosmic lighthouses. With massive dishes and sensitive receivers, radio telescopes capture signals invisible to the eye. Each pulse is converted into data, revealing rotation speeds, magnetic properties, and even the star's location in the galaxy. By mapping these pulses, scientists can chart the distribution of neutron stars and understand their behavior over millions of years. Radio telescopes turn quiet whispers into stories, letting us eavesdrop on the universe. Through them, we learn that even in silence, neutron stars speak, telling tales of creation, motion, and cosmic endurance. Fact 78. X-ray and gamma-ray emissions. From the surface, neutron stars often glow in X-rays and gamma rays, invisible to the human eye but brilliant to specialized instruments. These emissions come from hotspots on the star's surface, magnetic activity, or material falling onto the star from a companion. X-rays trace the energy of the star's magnetic fields and rotation, while gamma rays hint at extreme particle acceleration near the surface. Observing these signals allows scientists to understand the star's structure, spin, and environment. Even though we cannot see this light directly, it illuminates the star's presence, revealing its secret like a soft glow behind a curtain. The neutron star becomes more than a distant point. It becomes a living, energetic object whispering across the void. Fact 79. How scientists listen to pulsars. Pulsars are the universe's natural metronomes. Their regular pulses allow scientists to listen in rhythm, tracking time with astonishing precision. Each pulse is a heartbeat, marking rotation, energy emission, and even subtle changes caused by glitches or starquakes. By recording and analyzing these pulses, researchers can detect gravitational waves, test theories of relativity, and even map the space between stars. Pulsars provide a natural cosmic laboratory, where timing and observation unlock mysteries of physics. Listening to a pulsar is like eavesdropping on the steady pulse of the cosmos, a reminder that even the smallest stars have a rhythm, a voice, and a story to tell. Fact 80. Mapping the universe. Using pulsar timing. The regular pulses of neutron stars allow scientists to map the universe with incredible precision. Variations in arrival times can indicate gravitational waves, interstellar gas, or the star's motion through space. By combining data from many pulsars, astronomers can trace the structure of the Milky Way, detect invisible mass, and even create timing arrays that function as galactic-scale detectors. Pulsar timing transforms distant stars into cosmic landmarks, guiding our understanding of space, time, and gravity. It is a quiet yet profound tool, turning the subtle beat of neutron stars into a map of the cosmos. Through these pulses, we connect the infinite reaches of the universe to the patient observations of humans on a tiny planet, a gentle reminder that we are part of something vast, rhythmic, and eternal. Fact 81. The most famous neutron star, the Crab Pulsar. Among all neutron stars, the Crab Pulsar shines as one of the most famous. Born from a supernova observed on Earth in 1054, it spins rapidly, sending pulses of radiation across the galaxy like a cosmic lighthouse. From telescopes, we see its steady beat in radio, X-rays, and gamma rays, a rhythmic heartbeat marking centuries of existence. The Crab Pulsar is not just a star, it is a living monument to the explosive forces that create neutron stars and the enduring rhythms that follow. Observing it, we can imagine the energy of a star condensed into a sphere no larger than a city, spinning relentlessly, silently announcing its presence across thousands of light years. Fact 82. How old the Crab Pulsar really is. Though its supernova was recorded nearly 1,000 years ago, the Crab Pulsar itself is older. Its progenitor star lived millions of years before collapsing, quietly gathering mass and building the elements that would one day explode in brilliant fury. From its formation to now, the Crab Pulsar has been spinning, glowing, and sending out pulses that travel across space, untouched by the passage of time. Its age is a gentle reminder of the continuity of the cosmos, that events unfolding over human lifetimes are only fleeting moments for stars that endure across millennia. Through it, we glimpse a timeline far beyond our own, a quiet story of birth, death, and rebirth in the endless expanse of space. Fact 83. The youngest neutron star ever found. Astronomers have discovered neutron stars even younger than the Crab Pulsar, mere decades old in cosmic terms. These newborn stars are energetic and wild, spinning at extraordinary speeds and radiating intense X-rays and gamma rays. Witnessing such stars is like observing a newborn heartbeat of the universe, raw, powerful, and filled with potential. Their rotations are dizzying, their magnetic fields immense, and their existence a living testament to the violent beauty of stellar death and creation. Young neutron stars remind us that even in the cold, vast cosmos, new rhythms emerge constantly, carrying the energy of stars into space with relentless grace. Fact 84. The oldest one. Still spinning. Some neutron stars have endured for millions or even billions of years, yet they still spin. These ancient pulsars have slowed considerably compared to their youth, yet they continue to send regular pulses, whispering across the galaxy with quiet persistence. Observing them is like hearing an old metronome, ticking patiently through the vast silence of space. Their longevity shows how stable and enduring neutron stars can be, holding together against gravity and cosmic forces, quietly marking the passage of eons. Even in their old age, these stars shine with purpose, a serene reminder that endurance itself is a form of cosmic beauty. Fact 85. How new telescopes keep finding more each year. Each year, new telescopes and instruments uncover more neutron stars, many hidden until now in faint radio waves or X-rays. Advanced detectors peer deeper into the galaxy, capturing the subtle rhythms of distant pulsars and revealing systems that were once invisible. Every new discovery adds to our understanding of neutron stars' diversity, from tiny millisecond pulsars to young, energetic spin beacons. It is as if the universe quietly releases a new secret each year, allowing us to witness stars that have existed in silence for millions of years. These discoveries remind us that the cosmos is vast, mysterious, and generous, always offering new stories, new rhythms, and new connections for those patient enough to listen. Fact 86. How neutron stars enrich the universe with heavy elements. Neutron stars are cosmic alchemists. When they collide, they forge elements heavier than iron, including gold, platinum, and uranium. These collisions scatter material across the galaxy, seeding space with the building blocks of planets, rocks, and even the metals we treasure on Earth. It is a quiet, patient process on a cosmic scale, energy, matter, and motion combining to transform one form of existence into another. In a way, every piece of precious metal tells a story of ancient stars spinning, colliding, and scattering their remnants across time and space. Neutron stars are not just dense spheres, they are creators, silently enriching the universe while we look up at the night sky in wonder. Fact 87. Their role in forming planets and life's building blocks. The material thrown off by neutron stars eventually drifts into interstellar clouds, mixing with gas and dust. Over millions of years, these clouds can collapse into new stars and planetary systems. The elements forged in neutron stars become part of rocky planets, oceans, and even the molecules that make life possible. In this way, neutron stars are cosmic gardeners, scattering seeds that grow into planets and the chemistry of life. Each spin, flare, and collision has the potential to shape worlds far from their origin. It is humbling to realize that the gold in your jewelry or the calcium in your bones may have once been part of a neutron star, a tiny dense remnant of a long-gone stellar explosion, now woven into the fabric of life itself. Fact 88. The gravitational waves. They send across the cosmos. Neutron stars are storytellers of gravity. As they orbit or collide, they send out gravitational waves, ripples in space-time itself, stretching and squeezing the universe ever so slightly. These waves travel for millions of years, passing through stars, planets, and voids, carrying information about mass, motion, and energy. When they reach Earth, they are faint but measurable, allowing scientists to hear the rhythm of the cosmos and study events that occurred long before humans existed. It is a cosmic heartbeat, subtle yet profound, reminding us that even in silence, the universe communicates, and neutron stars are among its most eloquent messengers. Fact 89. Their influence on nearby stars. Neutron stars do not exist in isolation. Their intense gravity and magnetic fields can affect nearby stars and interstellar matter, tugging at gas clouds, redirecting paths, or even accreting material from companions. Some neutron stars pull in matter, forming swirling accretion disks that shine in X-rays. Others bend the trajectories of stars nearby, subtly reshaping clusters or binary systems. In this way, neutron stars are both dancers and choreographers, moving with the universe while influencing everything around them. Even small motions can have long-reaching effects, a reminder that the presence of one tiny dense star can ripple across light-years of space. Fact 90. How they shape the space around them. Neutron stars shape space itself. Their gravity warps space-time, and their magnetic fields twist particles into streams that flow outward at nearly the speed of light. Surrounding gas and dust are sculpted, radiation streams illuminate their paths, and entire regions of the cosmos feel their subtle yet profound presence. In effect, they are architects of their neighborhood, invisible hands shaping matter, energy, and light in patterns dictated by extreme physics. Even in their quiet spinning, they exert influence, a testament to how small, dense objects can hold enormous sway over the cosmos. Neutron stars are reminders that influence does not always come from size or brightness, but from persistence, intensity, and the quiet power of physical law. They are silent rulers of their corner of space, sculpting the universe with grace, mystery, and quiet majesty. Fact 91. The thin nebulae formed by their winds. Neutron stars send out winds of charged particles at incredible speeds, shaping delicate nebulae around them. These wisps of gas and plasma glow faintly in X-rays and radio waves, forming ethereal halos that stretch across space. From afar, these nebulae look like thin, flowing ribbons, tracing the invisible energy of the star. The winds sculpt their surroundings, carrying matter, energy, and magnetic influence into the void. It is as if the neutron star leaves a gentle signature, a mark of motion and presence that persists long after the initial supernova has faded. These nebulae are quiet masterpieces, cosmic brushstrokes revealing the star's influence on the space around it, a subtle yet beautiful trace of stellar life. Fact 92. Why they're key to understanding black holes. Neutron stars are the universe's boundary markers, teaching us about the limits of matter, gravity, and density. By studying them, scientists can understand the fine line between a neutron star and a black hole, where gravity overwhelms all other forces. They are laboratories for extreme physics. Observations of their mass, spin, and structure help researchers test theories about matter under conditions far beyond Earth's reach. Each neutron star observed provides clues about the ultimate fate of the most massive stars and the nature of space-time itself. In this way, neutron stars act as guides, showing the thresholds where matter bends, collapses, and transforms, illuminating mysteries that black holes alone cannot reveal. Fact 93. How they help test. Einstein's theories. Neutron stars are natural laboratories for Einstein's general relativity. Their intense gravity and rapid motion warp space-time, creating measurable effects like time dilation, orbital precession, and gravitational waves. Binary neutron stars in particular allow precise tests of these predictions. Observing their pulses and motion, scientists can measure tiny deviations and verify that Einstein's equations hold even under extreme conditions. It is a remarkable partnership between theory and observation, the universe itself providing instruments and experiments that humans could never recreate. Neutron stars remind us that the cosmos is both mysterious and intelligible, following rules that can be understood if we are patient enough to listen. Fact 94. Why they act like cosmic laboratories. Neutron stars are extreme, isolated, and predictable. Perfect cosmic laboratories. Their density, rotation, magnetic fields, and energy emissions create conditions impossible to replicate on Earth. From studying pulsars to observing magnetic flares, scientists explore physics at the edge, superfluidity, superconductivity, and matter compressed beyond atomic limits. Each neutron star is a natural experiment, offering insights into quantum mechanics, relativity, and the behavior of matter under the most intense pressures. They are reminders that the universe itself conducts experiments on scales and intensities far beyond our imagination, quietly revealing secrets to those who observe with patience and care. Fact 95. The secrets they may hold about dark matter. Some scientists believe neutron stars could help unlock mysteries about dark matter, the invisible substance that permeates the universe. Their gravity, density, and interactions may reveal how dark matter behaves, or even how it accumulates in extreme environments. By studying subtle shifts in rotation, energy emission, or gravitational waves, researchers hope to catch hints of this elusive cosmic ingredient. Neutron stars may serve as detectors, sentinels, and clues, quietly holding answers to questions that have puzzled astronomers for decades. Even in their stillness, these dense stars are active participants in the universe's unfolding story, bridging the seen and unseen, the known and mysterious, reminding us that the cosmos is full of hidden depths waiting to be discovered. Fact 96. How many neutron stars may exist in our galaxy? Our Milky Way may be home to hundreds of millions of neutron stars, though only a fraction are visible to us. Most spin silently, radiating faintly or not at all, hidden in the dark vastness of space. Each one is a remnant of a once brilliant star, carrying the legacy of stellar life, explosive death, and transformation into something denser and smaller than a city. Though they are tiny on a cosmic scale, collectively they form a network of hidden energy, silently influencing their surroundings. It is humbling to imagine how many of these cosmic survivors exist beyond our sight, each a quiet testament to the universe's cycles of creation, collapse, and endurance. Fact 97. The possibility of neutron star planets. Some neutron stars are orbited by planets, remnants of the star's pre-explosion system, or formed from material captured after the supernova. These exotic worlds exist under extreme conditions, gravity far stronger than Earth's, radiation intense enough to light them from within, and magnetic fields twisting space around them. Though inhospitable, these planets remind us that the universe finds ways to persist. Matter clings, forms, and arranges itself even under the most hostile circumstances. Neutron star planets are cosmic curiosities, proof that creation often follows destruction, and that even death can give rise to new forms of existence. Fact 98. Whether humans could ever visit one, and why not, neutron stars are beautiful but deadly. A single teaspoon of their matter weighs billions of tons, and their magnetic fields, radiation, and gravity make any approach impossible for humans or spacecraft. Even getting close would be catastrophic. Tidal forces would tear apart anything nearby. Yet, in imagination, we can travel there. We can spin alongside them, watch pulses flash across space, and feel the rhythm of the cosmos without leaving Earth. In dreams, neutron stars become places of wonder, a reminder that exploration is not always physical, and understanding can be achieved through observation and imagination. Fact 99. The unanswered mystery scientists still chase. Despite decades of study, neutron stars remain full of mysteries. What exactly lies in their cores? How do superfluid layers behave? Could they reveal clues about dark matter or quark matter? Every pulse, glitch, or flare is a whisper of the unknown, an invitation to keep learning, observing, and questioning. Scientists chase these mysteries patiently, guided by curiosity, instruments, and the subtle signals of distant stars. Neutron stars remind us that the universe is never fully revealed, and that wonder is a force as enduring as gravity itself. Fact 100. The poetic beauty of these tiny cosmic giants. Neutron stars are tiny giants of the cosmos, dense, powerful, and full of secrets. They spin, pulse, collide, and radiate, shaping the galaxy and inspiring awe in those who observe them. Though small in size, their influence stretches across light years. They are cosmic lighthouses, alchemists, laboratories, and storytellers. Every glitch, flare, or pulse carries a narrative of birth, death, motion, and transformation. As we drift asleep under the night sky, it is comforting to know that these tiny giants continue their silent dance. They are reminders that even in the densest, smallest objects, there is beauty, rhythm, and enduring magic, a quiet poetry written in the language of the universe itself,